Hello everyone, and welcome to AISC's webinar, The History of the AISC Specification, presented by Ted Galambos. Today is January 22nd, 2016. My name is Christina Harbour. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce today's speaker. Ted Galambos earned his PhD in Civil Engineering from Lehigh University in 1959 after receiving both his bachelor's and master's at the University of North Dakota in Grand Forks. Dr. Galambos taught and researched at Lehigh University, Washington University in St. Louis, and ultimately the University of Minnesota, where he currently serves as Emeritus Professor of Structural Engineering. He is also a registered professional engineer. Dr. Galambos was elected to the National Academy of Engineering in 1979, which is one of the highest honors accorded to engineers. Among his numerous awards, he has received the T.R. Higgins Lectureship Award and the Gerhard Higher Educator Award, both from AISC. He has been involved with the AISC's Committee on Specifications for more than 40 years. He has been involved with research on steel structures since 1956, and his work has influenced a number of aspects of the AISC specification. Welcome, Dr. Galambos, and I will let you take it from here.
Hello, audience. Greetings. I'm going to speak about the informal history of the AISC specification. My source for this talk is the perusal of the various versions of the specification and personal memories. And the reason for this work that I had a lot of fun doing was that AISC is going to be 100 years old in 5 years, and that's not a very long time, and the AISC specification is going to be 100 years old in 2023, and myself and a few others still living have been involved in the life of this document for most of the second half of its existence. So it's time to remember before I forget. As you can see, the time is creeping up on me, and but I'm still smiling. The story starts in September 1, 1956, when I reported as a graduate student at Lehigh University to Lynn Beadle. John Fisher and I met at 8 o'clock in the Fritz Lab parking lot and reported to Lynn Beadle immediately up on the 5th floor of Fritz Lab. And that began my involvement with the AISC specifications. The reason that I was selected for the graduate work was that in my resume they found that I could speak, read, and write German. And they needed the translation of the recently appeared German buckling specification in preparation for a new AISC specification and I guess a background for introducing effective lengths. So here I am, somewhat of an institutional memory, an old guy trying to remember. Now, why was it important to have a new specification? And it was an important fact because the Secretary of Commerce wrote a very nice letter to AISC on the formation of the institute, and this was Herbert Huber, who eventually became president, and he was, of course, also an engineer. The inaugural meeting listed the following objectives: the establishment of a single code authority that would be recognized by building code authorities and designers to eliminate the confusion that existed in the construction industry caused by the numerous and different manuals, each containing proprietary information. And somewhere in my voluminous library, I have a whole number of these. The first AISC specification was a pretty little document contained in a little pocket volume that had 23 pages, and it contained the steel design spec, the ASTM spec, and design aids. The actual spec was 9 pages, and it cost 25 cents. So it was a real deal. Now, the specification was written by 3 groups of people: 2 professors, 2 structural engineers, and an architect. And I think the further developments with an advisory board for the specifications kind of represent the same kind of a distribution. The specification was, in today's language, I would say, a true performance-based specification. And the requirements for a satisfactory structure were the material must be suitable, of uniform quality, without defects affecting the strength or service of the structure. And the computations and design must be properly made so that the unit stresses specified shall not be exceeded, and the structure and its details shall possess the requisite strength and ductility. I wonder if we really would need any more than this. Now, at the time this was written, a lot of things that we now know and use have been already developed. The mathematics was already in place over 100 years before that. Theory of elasticity was 30 years before that, and a lot of the theorems, Betty's principle, and all of those things were known. So we were not talking about starting into the jungle from the beginning. The major headings of the spec are very familiar to what we have now: beams and girders, combined stresses, rivets and bolts, connections, lattice, minimum thickness, and so forth. So there's the outline was already here for what we now have in our specification. About 7 years later, the AISC put out its first manual, and it contained the specification, but it also contained a lot of tabular materials for cross sections and sort of a textbook explanation as to why some of the rules were in the specification: beams, columns, and so forth. So this was cost $2, and it was 476 pages long. So it's not that much different from our present manual. Well, it's about half the thickness, okay? And the main argument for a new specification was that everybody did what they thought they wanted to do, and the main problem was that there was a bunch of column curves and column formulas in use, and they were about, depending on where you are, the strength was different by about 10 KSI. And the book says very clearly that the diagrams clearly illustrate that the basic unit stress is not a consistent index of the so-called factor of safety. And you can already see that they called it a so-called factor of safety. So, and this carried over into a lot of other things that were used in design. Let's look at the development of the column formula that was used. The first column formula is shown here, and it was in use maybe pretty close to 50 years. And it's a formula that was developed first in the middle of the 19th century in England by RANKINE, and the limit state was the attainment of first yield of a column with initial imperfections. And below an L over R of 60, you didn't worry about column strength, but worried about local crippling. And after that, you have this column strength. And if you would scoff at the idea of this as a limit state, I would like to tell you that the limit state that the European column formula is based on is exactly the same limit state as was produced by Rankine in the 1850s, and it certainly does not reflect the work that was done later on to the tangent modulus solution and the nonlinear behavior. And here you have just a picture of the two columns. They're all nice riveted columns and look kind of interesting. And here you have a bigger picture of the herd of column curves. Just imagine how much fun it was to teach that. Now, the major changes in the specifications are shown in red here. And the changes were due to the need for new technology, new practices, new research. In 1961 to 63, there was a radical change. I say 61 to 63 because the 61 specification had some things that had to be corrected, so the 63 specification in the light brown cover is the one that really counts. This was a radical change because a large committee was formed and locked up at a resort in Michigan for a week. I wasn't part of this because I was still a little too junior for this. But this is where the research that had been done previous to this time in the 1950s and earlier at Lehigh and at Illinois, and that was then put into the specification, and also to the chagrin of many, the idea of effective length was introduced. This then was improved through to 1989, and that was sort of the end of the stress era, and then the strength era started with the first LRFD specification in 86. But the big changes that took place, I think, were the ones in 61 to 63. Here you have how things became fatter and fatter and fatter, and both in the specification and in the commentary. And the reason for this is that newer technologies came in, new research came in, and new constituents, and I think especially the emphasis on slender elements that were brought in by the metal buildings people whose structures did use slender cross sections. And so I think slender is beautiful. And the committee members are basically constant in number, and they're pretty much evenly distributed between professors or researchers, I guess, and then fabricators, manufacturers, and consulting engineers. And this is a very august group, and it meets twice a year, and its subcommittees meet more often. The main feature of these committees, this committee, is that it's a consensus committee, is that everybody has to sign off. And there is no possibility for saying, well, 90% of the people think this is safe and 10% don't. Well, this is not going to work. Okay, now, oops, that's not what I need to do. Okay, the material that we had to work with, oops, yeah, the material that we had to, okay, all right. Oop. Okay, we have a little, okay, I'm sorry, I got mixed up here. The material we had to work with in the beginning was just carbon steel, first with a yield strength of about 30 KSI. Then we got more confident, went to 33 KSI, and then we went to 36 KSI, and it's all pretty much the same stuff. But in 1961, the heavens opened, and we were allowed to use a whole lot of steels, and then of course now we are using the basic steel as 50 KSI, and I'm not sure that that's a whole lot different from the previous steels that we had. We just have more confidence and more quality control. So that was a very big introduction in 61. This is the column curve, as I talked to you before, and it was from 23 to 36. It was a very simple two-branch curve, and then this was changed in 36 to 61. This is what I learned when I was an undergraduate. We have a sort of a parabola for L over R less than 100, and then we have the Rankine curve with a little input, a little ice cream put on it. So between 120 and 200, and we called this secondary members and this primary members. Now we've gotten away from that, and we don't do secondary and primary members anymore. And then in 1961-63 and until the end of the stress era, we have used this formula, and this is the inelastic part, and this is the elastic part. This is the Euler formula with a factor of safety, and this is the average curve between the tangent modulus of strong axis and weak axis buckling for wide flange shapes, W8 by 31. That's the basic member that was used, and this was this time not just a formula that was cooked up in a by researchers, and then but there was also a pretty extensive experimental program that went with that at Lehigh University. So this took care of the material nonlinearities, and in hot rolled steel, this was the residual stresses. The factor of safety varied from 5/3 to 23/12, and it was supposed to empirically take care of initial imperfections. The origin of 23/12 is pretty obscure, but maybe it could be found in the book of Numbers in the Bible. I don't know. But that's where we, most of us, learned and taught. Now, and here you see the comparisons between the 36 and the 1936 and the 89, and then our present column curve. The present column curve takes care of both initial imperfections and the residual stresses, and it is based on research that Radar Bierhoefde performed for his PhD thesis at Lehigh, and it is the average curve for all of the tests that were performed and that were then reanalyzed. And the simple formulas that we ended up with are due to Ray Tide, who came up with the formulas that we're using. So that's where this is. And column curves, of course, are very important. They are like a flag in a country, and a new country always starts with getting a flag and then getting a column curve. And it is also very important to note that the British had a different philosophy and different column curve in 1939, and the Germans had again something very different, and they went to war with each other, and you figure that out. Okay, now let's look at lateral torsional buckling rules. And it started out with the Rankine formula with a little bit increased beginning allowable stress. Then it was increased a little bit more to more confidence in what was done. And then in 1949, a new column formula was introduced, and that's the LD over BT formula. This was as a result of research conducted by Carl de Vries at Bethlehem Steel, and his paper in the AISC specs, the AISC Structures Journal is quite an interesting version of exercise, and it's quite convoluted, but he came up with what turned out to be one of the right parameters. And the result was that we really had a very, very conservative situation on our hands. Now, our friend George Winter at Cornell University, he was a member of the AISC Specification Committee, And he was a very, very astute and he had this gruff old Austrian accent. And he said, now just wait a minute. Timoshenko had all of this figured out a long time ago. And he referred to Timoshenko's book in 1936. And here you have the elastic buckling formula that we are now using. Some of the numbers were substituted in there, and so but this is it. And you can take this apart into two stresses, the subvenant buckling stress and the warping restraint buckling stress. And if you do a little cooking around and substitution, you get these two formulas. This is the Euler formula. This is the LD over BT formula. And if you just take that and take 6/10 of it for the yield stress, there you are. And George Winter was very kind to point this out to all of us. Okay, now this was then put into the new equation, a new specification in 61, and here you have the LD over BT formula, and here you have a parabolic formula, and then we said, okay, we'll take the maximum of these two, and which will be less than the square root of the sum of the squares. So why we were afraid to do that, I have never known, and it was a heck of a difficult thing to convince students that now this time you use the maximum rather than the minimum. And you know, the slide rule would have done this very nicely. This was then further extended and evolved, but it still stayed the same until 1989, and it was changed in the 1986 LRFD formula, and of course we're not using this anymore. And here you see the curves and the bulge on the elastic part. So that's lateral torsional buckling. Now let's look at the combined stress. That's another big issue. And in the beginning, we just added the axial and tensile stresses, and the bending stresses, and took the minimum, compared them to the minimum of the allowable stresses in compression and tension. And this was thought to be a little bit too primitive, and in some meetings in, I'm sorry, that should be 1949. Oh, I'm sorry. You better fix that. Anyway, the the formula was an interaction formula of ratios, and the legend has it that Ted Higgins of AISC, who was one of the big leaders and research engineers of AISC, did it on the back of an envelope in a committee meeting. And of course, this was further elaborated in the 61, 63 specs, in which we introduced the C sub m factor for the moment gradient, and the reduction formula 1 over 1 minus FA over FE prime, and FE prime contained the infamous effective length. I'm calling it infamous because everybody else does. I kind of like it anyway. But so this was than what we ended up with until we had the new formulas in the LRFD specification. This was extended to the biaxial case, and that's what we ended up with in 1989. Okay, let's look at some of the other things that have changed. The slender cross-sections were introduced in 1969, but before that we had B over T of 12 first for beam flanges. Then in 36 we went up for beam flanges to B over T of 16 and H over T of 40 for webs. And then we kept the same limits in 49, but we chopped off for our cross-section calculations the parts that exceeded these limits. So it was kind of a butchering of the cross-section. In 63, we left the same limits, but accommodated the other state grades of steel. In 69, we introduced the Q factors for the effective width, for the unstiffened elements, and the effective widths for the stiffened elements, and that we took over from the cold form specification. Now, I kind of enjoyed the Q sub S factors and so on, but progress moves on, and you can go to the funeral of the Q sub S factors in the 2016 specification. It's done. Other things that changed, we had 1/3 increase of the allowable stress for wind, and then later earthquake too. That has disappeared because of the load factors in AISC 07. Fatigue came in at 36, and there's a great deal of research at Lehigh with John Fisher and his colleagues. Plastic design came in 63 in a real big way, and not only as a separate section, but also in the permission of moment redistribution and in the increasing the allowable stress. Types of construction: simple, rigid, and semi-rigid. Ponding was asked to be taken care of, and a lot of help was given in the specification because of some failures here, and the same for vibration. But of course, vibration was it was told, okay, you take care of it. We're not responsible if your floor wiggles too much. The deflection was also introduced again as a thing, as a monetary issue, and said, well, you take care of it, and if you have troubles, we're not responsible, but we're not going to give you any numbers. And that was because a lot of the practicing members of the committee wanted to keep this open for them. Web-tapered members came in after a whole lot of research at Buffalo University with George Lee, and that disappeared, as did hybrid girders, but these are back now in the AISC practice manuals or design aid manuals. Now, composite beams, as we understand them, came in 63, although encased beams were treated before that, and incomplete composite action, which gave you a lot of um, economy came in 69 as a result of research, and then you have the metal decks came in 78. Welding and high strength bolts came in 49, and friction connections and so on. So this stuff is mainly due to research at Illinois and at Lehigh with John Fisher and his colleagues, John Rumpf, on the bolted connections, and there's some huge connections in the 5 million pound testing machine. And in fact, when those connections went, we had to, before that, we had to excavate not excavate, but we had to get out of the building before the exploded energy was released. And, you know, it was quite a big bang. And the combined rivets and bolts and then welds was in there, and it still seems to be causing some stomachache to various people. And web crippling and all of those things came as a result of research conducted at Lehigh in the 1950s. I remember all night 24-hour-long sessions manning a manual hydraulic pump while the axial load was provided by the 5 million pound testing machine. The plate girders went from riveted plate girders to welded plate girders, again as a result of a major project at Lehigh with Conrad Basler and Bruno Thurliman. Conrad Basler is still active and living, and he was quite a guy to supervise this work. And it was interesting to see during the fatigue tests the breathing of the webs. It's like a running dog. It was a real interesting thing. And of course, these standards here for riveted plate girders were very, very conservative. And here the unspeakable thing happened that the elasticians would turn around in their grave, that we permitted buckling and used post-buckling strength. Block shear was a result of failures. Compactness limits also came in, was a very handy thing. And then you have block shear. We had torsional buckling, and of course including work on angle beams and angle columns. The angle beam work was done by Max Lay and John Lee at the Broken Hill proprietary company in Melbourne. Then, of course, we had the increased stress, basically saying you could have a plastic moment at the end of an elastic analysis, slender Q factors and so on, and the effective length factor that took care of a lot of second order effects and resulted in also a lot of research to get around the effective length factors, and you have George Madon Sherman and Joe Ura and others have brought up out of this the direct design method, and effective length in 2016 is kicked to Appendix 7, I think, and I would say as soon as I'm dead for the following specification, it probably is going to be pushed out into the unknown blackness of forgetfulness. C sub B factors were introduced here also. Anyway, this was just a small view of the original plate girder design, where you choose the whether you need stiffeners and the spacing of stiffeners and then the allowable stresses. Now, this AISC from the very beginning had a great deal of interest in research, and actually, if you ever get a hold of this book, the first 60 years, it gives you so much of the first 50-year history of the... Anyway, they were interested in fireproofing, welding, bracing. Hey, that's a subject that's been around a while. Then different types of steel, and then political things. The noise abatement of riveting, I guess that just irritated a lot of people, and it's just like a vibration, jiggling the teacups. So height of building restrictions is again political, and this is also speed of erection was a political thing. But the motivations for change, you can see here you have industry motivation, composite design, high-strength bolts, welding, connections, different steel grades, and so on, came from industry, and academia came with plastic design, stability criteria, computer methods, direct design, bracing rules, plate girder design, fatigue, fracture. Ponding actually should be over here because it was the research was done by AISC, one of the AISC engineers. And so you have the two paths, and this is still active today. The example would be, and I just list one of these, that composite beams came into being in the 1930s already. In fact, a number of bridges in the German autobahns in the 1930s were composite beams. After the war, there was research at Illinois and at Lehigh. At Illinois was mainly Ivan Viest, who was again a member of the AISC committee, and at Lehigh it was Bruno Furliman. Charlie Culver, as an undergraduate, did a tremendous job of refuting the Illinois gospel that was an elastic cross-section, and the Lehigh cross-section was the plastic moment cross-section. Then the big occurrence in 59-61 was the Asho Road Test at Ottawa, Illinois, where a battalion of soldiers from the transportation service spent a couple of years driving trucks over bridges and pavements. John Fisher worked there, Ivan Viest, my brother Charlie worked there, and I was there visiting once to see a composite bridge gradually sag as the army trucks went over slowly. And there was this book by Viest and Fulton and Singleton. They made composite design popular. First standard, Asho was 57, and the T was added later. And AISC specs in 63 and This is still with us. And then the last example I want to talk about is plastic design, and this is new from the early 1900s. The first inelastic behavior was recognized for columns by Engesser with a tangent modulus in Switzerland, and then the first plastic continuous beams, or actually fixed end beams, were tested at Budapest, and the idea of a plastic hinge was proposed. And those of you who know Hungarian, the title of the paper was Kísérletek befalazott. So there you are. But a lot of good things come out of Budapest. And then in the 1930s and 40s, John Baker in England, Cambridge, did a lot of tests on plastic design and on the inelastic instability, and got a specification, built a building, and in fact he did all of this against the members, or some of the members of the International Association of Bridge and Structural Engineers, and one of their speakers was a professor at the Federal Institute of Technology at Zurich, Stüssi, who said that plastic design was for imbeciles and communists. So there. So, but plastic design was brought over by John Baker. In fact, he and Ted Higgins and Lynn Beadle, those were the Ted Higgins from AISC and Lynn Beadle at Lehigh, brought plastic design to Lehigh and did an awful lot of research. Baker visited here. Lynn Beadle spent a year in Cambridge. So did Bob Ketter, who was my thesis advisor. And there was a lot of work that was part of the new specification. And what we learned in the 50s and 60s, 70s, that plastic design leads to a better understanding under load, gives economy, and it's beginning to be used more and more in seismic design. And even if you don't, you should study it, because then you won't be afraid of your structure. That's my reason for teaching it. Inelastic instability is much more difficult, so you had to have a study of that with plastic design. Theory and testing wasn't enough, or testing had to be part of the development. You can do all kinds of sins in the name of elasticity, but in the plastic range you have to test. And what was drummed into us by Beadle, that the results must be directed to usefulness in practice. And we traveled many, many times from Bethlehem to New York, 101 Park Avenue, to talk to the Welding Research Council and to Ted Higgins, and it was a great life. And so I think this was, there were many, many applications of this, and I think eventually, these are just a few highlights. We had frame tests, braced and unbraced frames. Joe Ura worked on this, and before that we had tests on gabled frames with George Disco, and we had two conferences at Lehigh where participants were involved with the testing that we did, I think that there are still Larry Kleiber is one of them who was there, and many of the others are still living who were there. Then we had the element stability with thickness limits, Jerry Heyer's work, who was later Vice President of Research at AISC. Then I did work on inelastic lateral torsional buckling, and so did George Lee. Frame stability and effective length of Bernie McNamee and Li Wu Lu. It's kind of interesting to see a frame buckling. It's really neat. And I did a lot of tests on beam columns, braced and unbraced, and with Max Lay. So that was sort of a life that we had. And then, just briefly, I won't get into my hobby horse about LRFD, but I think that it was a great life and it was fun. And I want to thank you very much. This is my favorite bridge. It's over the Danube in Budapest. It was built in the 1940s, designed by an Englishman, Clark, with an E at the end, and the local construction engineer was an Englishman, Adam Clark, with an didn't have an E at the end of his name. And I was born in a hospital somewhere out here. Well, thank you very much.
Thank you, Ted. And let's see if we can answer a few questions from our viewers. As a reminder, if you have not sent in your questions, you may still send those in by chat.
How do I?
Okay, the first question that we have, I'm going to take us to slide 25. Whoops, excuse me. On slide 25 here, you have 1986 coming after 1989. Is there a reason why you've sorted the years?
Absolutely, because the light came on in 1986. That's when we had the first LRFD specification. And we had 3 of those in 86 and 93 and in 99. And then these specifications were put together with into the current specification with the combined LRFD and the allowable stress design specification. So 89 and 86 overlapped. The 89 was the green book.
Okay. And speaking of that green book, we have a question on that. This person wants to know, in some industries, the LRFD method is not seen as the best option for analyses and design. For example, the industry I work in relies on the AISC 9th edition. Do you see the LRFD system as being the best option for all industries?
Well, I tell you, you're asking the wrong person. Obviously, I think LRFD is more rational, and I think that, both of those specifications are providing safe designs, but I mean, this is prejudiced, okay? Now, I think that the 89 specification is at you're looking at the working stress level, and the present specification looks at the ultimate strength. So you are looking in the 89 spec at a headache, and then in the present specifications you're looking at cancer.
Okay. while we're on this slide 25, and you're talking about the evolution of the specification, the question is, do you feel that the evolution of the specification was due to the need for increased safety, reduced costs, or both, or something else?
No, I think that the specification was always concerned about economy. So that's a given. The increased number of provisions reflect the wider use of the specification by more different industries and also with new factors coming into play. You know, the composite design was a very big part of the specification. The specification also has the part on HSS and their connections. That's a very large increase. And then we have a whole bunch of things on slender elements. We've added a part on fatigue that's quite extensive, and on fireproofing, and on bracing. So there are a lot of things in there that before weren't used. So no, it's development of the industry, and not so much for trying to make things fat.
Okay, thank you. And the next question we have, someone is asking if you remember a specific test. Do you recall a full-scale truss test in a John Deere factory building in Davenport, Iowa, many years ago? I was a structural engineer for John Deere at the time. You were wearing a three-piece suit and sneakers. The sneakers were appropriate because when the truss failed, we all were running. Do you recall this experiment? And
Davenport, Iowa. Okay, I think this was a truss test on a steel joist floor system, and I recall that the first compression member buckled, and I think that as a result, I was a consulting engineer for the Steel Joist Institute for, I think, 34 years, and we made a lot of changes in the specification as a result of that test. It was an embarrassing test because we had all of the executives from this particular company there standing around, and it was, yeah, I remember that.
I'm sure it was exciting.
I think I know who asked that question.
The next question is, what is the status of plastic design today?
The status of plastic design today is that I think that in many instances it would be very useful and very economical to use under the static loading, but it's greatly used, I think, I know in seismic design, that it is, I think the design that takes the pushover tests into consideration is all plastic design, and the seismic designs, the general seismic designs, take implicit account of the plastic behavior, and plasticity is used in seismic design to eat up a lot of energy. So It's a something that is used in some industries, and some engineers stay with the elastic behavior. But even if they think they're using the elastic behavior, just think of it, they are still using the plastic moment as a limit state in an elastic design. So it's kind of inconsistent, but that's the way it is.
Okay, and then we actually had a few questions on this bridge. Was it built in the 1940s or the 1840s?
1840s,
The 1840s.
and this was the first bridge like this was built in 1828 in England, and this was one of the next bridges, and it was an I-bar bridge, and it had it was rebuilt after the First World War. It was, and then in the Second World War, in the December of 44, it was blown up by the Germans. The Russians were on this side, and the Germans were on this side. It was the siege of Budapest, and this was one of the first bridges that was then rebuilt after the war. All 7 bridges on the Danube in Budapest were blown up, and they were rebuilt, and all of them except one were rebuilt as by the original design, and the one was a new one. There was a suspension bridge. What's the other question on this?
That was it. And then our last question that we'll take: what advice for practicing engineers, researchers, and specification writers do you have as we move forward?
Keep on learning, keep on researching, and keep on getting better and better structures. And I think that the biggest challenge, and this is something that we're not really teaching that much, is to rebuild, to build a new bridge in the place of an old one, or to rebuild a harbor or a highway, or you know, this is the most tricky thing, in which you need to know the old, and then you need to know the new, and for that we need certainly a lot more steel design taught in our universities than is being done right now. End of preaching.
Well, thank you very much, Dr. Galambos. Unfortunately, that's all the time we have today for questions. If your question did not get answered, we will try to reach out to you by email with a response.